Hello everyone, welcome to this project demonstration on mold pattern matching in IC design using shape recognition. I'm Sathvi Baragur Karthikeyan. Um, so talking about pattern recognition, it is widely applicable in everyday life, from classifying organisms such as salmon and sea bass, speech recognition, text recognition, and many more. It involves identification of objects in raw data or otherwise recognizing hidden information in data. Pattern recognition involves the following tasks, namely classification, which involves obtaining the model inputs and making decisions based on regions of interest, features computed for this region, and the common everyday example is classifying between the salmon and sea bass. Segmentation, it involves identifying regions of interest, and parsing is learning search algorithm parameters for structural descriptions, just trees or graphs. Here we explain the application of pattern recognition and mold detection. Talking about mold detection, IC fabrication involves different kinds of molds at 8 stages, namely the Peeble, Envil, Active, and many more. The above set of masks are unique to each stages in the fabrication process, and pattern recognition could be our basis for identification of the mask based on the dimensions and shape. So here is an overview of the idea behind this project. Modern VLSI circuit chips require high amount of precision during design and fabrication, and precision is highly oriented to the mold fabricated. Here we attempt to show the application prospects of such pattern recognition and matching that can be used in VLSI. The recognition of geometric objects is done using an algorithm that takes in an RGB image and converts it into a two-dimensional black and white image. Pixel classification is done for object background separation. Area bounding box calculations are done to obtain metrics oriented with the object. The obtained metrics are then compared to certain metrics to decide on the kind of geometry. So we all are aware that an image can be defined as a function giving light intensity values at each point. And the points at which an image is sampled is called a picture element, or also known as pixels. The intensity values are integer values ranging from 0 to 255. For continuous images, they are found by averaging over a small neighborhood around the pixel location. Often the sampling grid is a square, and the relative distance between grid points often determine the fine details that can be resolved. This is one of the key criterions to image digitization. So our proposed methodology involves the following steps. Taking in the template of the mold, we convert the RGB image into a two-dimensional black and white image. We find the area, recognize the boundaries, and use a bounding box in order to find out the extent of the object. Calculating the ratio of the area of the object to that of the area of the bounding box, we get the extent. Based on the ratio metric calculated, we are able to classify the objects based on the geometry, and comparing the metrics to that stored in a database, which consists of comparing the template mold with that of one used during the fabrication processes, gives us the detail on the stage of the fabrication process and the kind of mold used. So starting with reading the image. First step involves reading the image, and this could be a bitmap file, a PNG file, or any other image file. A bitmap is a raster graphic image format, and it is technically characterized by the width and height of the image in pixels and by the number of bits per pixel. The image is a cluster of different mole units used during the fabrication process. Each is defined to have a unique height and width with respect to the stage at which it is used. They could be either rectangular or square in shape. Now, converting the RGB to a black and white involves extracting the luminescence of the RGB colors. And this is done because we eliminate the saturation and hue information of the intended RGB pixels. A threshold is then set and the luminescence of each pixel is compared with this threshold. All values that are greater than this threshold are replaced and taken to be white, and those which are below this threshold are taken to be black. Connectivity. To determine connectivity, we need to find the adjacency of 2 points in a digital plane. If the adjacency is defined by means of 4 points, then it's called 4-point adjacency, while if it uses 8 points, it's called 8-point adjacency. Such neighboring pixel detection is useful in boundary detection. For boundary detection, we place a single pixel on the object background interface as a starting point and move in a clockwise or a counterclockwise direction searching for the object pixels. The pixels may be searched either diagonally or in edge-adjacent pixels. By hunting for object pixels in a fixed direction, the object's boundary can be recognized. Challenges faced with respect to real objects. Patterns appearing as distinct clusters are less discriminable. Overlap between these distinct objects is common. Thus, we go for pattern classification by means of pattern classifier and segregation of pixels into classes. Definition associated with respect to pattern classifiers involve feature space, which is an n-dimensional space whose axis presents gray values. Feature vector. A feature vector locates a pixel in the feature space. Discriminant function. Function of the feature vector that provides probability that the pixel X belongs to a particular class, say I. And decision rule is a rule that assigns a pixel to a particular class. We use the k-nearest neighbor probabilistic approach. For boundary detection, we place a single pixel on the object background interface as explained before. The pixels that can be searched either diagonally or in adjacent pixels, we follow the hunting mechanism by using the k-nearest neighbor probabilistic approach. It has an advantage that is its intuitive operation. First, the distances between a single test sample and each of the training samples are calculated. The training samples closest to the test samples are defined as its nearest neighbors. The test samples is then assigned to the class from which a plurality of its k-nearest neighbors are from, where k is typically an integer less than 10. In addition to having to optimize the selection of only a single parameter k, the theoretical basis of the KNN is well described. Pattern separation by boundary detection. Pattern classification can be done by abstracting measurements of features from the pattern and classifying them based on those measurements. A simple technique is to classify a point in the vector space to the class associated with its neighboring pixels. Now consider a rectangle. We define 4 functions to determine the rectangular pattern that we wish to detect. Let phi1 of ij, phi2 of ij, phi3 of ij, and phi4 of ij represent the 4 vertices of the rectangle. The rectangle detection process involves that if any pixel belonging to this rectangle have a value of 1 for these functions. Also, the presence of desired rectangle is indicated if and only if this function is less than or equal to 4. Once the object boundaries have been recognized, the area of the object can easily be calculated by summing the number of pixels within the boundary extent. It is necessary to remove these pixels before furthering the process. They can be converted to background pixels, that is, they can be inverted. In this way, the image is filtered to remove small isolated noise pixels. The bounding box concept. The bounding box is an imaginary rectangular enclosing the object and having its sides parallel to the axis. It helps in shape recognition. The bounding box estimation is carried out in two steps. First, a fixed-sized window is used to infer the aspect ratio, and then the area is estimated. The ratio of area of an object to the area of its bounding box is called the extent. Each geometric shape has a definite extent value, such as for a circle it's 0.78 and for the triangle it's between 0.25 to 0.5. If the length and breadth are equal, then we infer that it is a square. These simple tests help identify the shape of the given geometry. So now, coming to the results using the proposed MATLAB code. So this is the algorithm. Here is the code. It begins with reading the image mol.bmp. Now this image is converted to a grayscale image, and then we perform the edge detection operation, and then we calculate the parameters such as area, centroid, and perimeter, and we use that centroid to identify the image of the object, and based on the dimensions we come up with the kind of mold. So as you can see, here are the basic geometric shapes: circle, ellipse, diamond, and ours are a rectangular or square shaped molds, and these are segregated into the various kinds of masks: P-Well, N-Well, P-Select, Active, based on the dimensions. Running this code, we get the following images. This is the original image, followed by the edge image, and then we have the final detected output, which rightly detects the various masks, namely poly, metal, active, P-Select, N-Select, P-Well, N-Well. Each of these masks have a definite dimension and a shape, such as the metal contacts are square in shape with definite dimensions, while the active are rectangular. The poly is also rectangular. They have dimensions which is specific to the kind of fabrication process, and their dimensions are in lambda units. So coming to this, these results have been explained in here. Now coming to the presentation, so we continue with our conclusion. So a number of shape recognition algorithms have been proposed in the past, and object recognition can usually be done in two ways. Either by comparing every pixel in the image to the pixels of a number of other images stored in the storage unit, or extracting information from the image calculating certain metrics based on those geometry of the image, and comparing these values to predetermined values. The first method is commonly used in fingerprint recognition or facial image recognition. However, this is memory intensive as well as time consuming. While the second method is very useful in terms of memory and time, while it could be code intensive. The algorithm discussed is very simple yet effective with the chosen parameters. The concept of recognizing shapes on the basis of easily obtained metrics has been extensively used in researches involving recognition of breast cancer cells from a given tissue sample, mammal classification, and many more. In our case, we present this algorithm to detect the shape of moles and the extent parameter in order to classify the geometry. As each mole in different stages of the fabrication process differ from one another in terms of dimension and shape, their extent values as well as their RGB content do not match, and we harness this to the advantage of recognition. The applications are not restricted to the application we have portrayed. In fact, they can extend to any field that require classification of different objects based on their physical appearances or dimension. This may include quality inspection in assembly lines, artificial robotic intelligence, computer vision, recognition of vehicles, to toll booths or traffic signals for traffic status determination, etc. Coming to the future work, each year billions of ICs are being fabricated and being used in a number of applications. So it is important to verify the IC fabricated being correct. This can save a lot of money, time, and human resource. We discuss about mole detection that are different at various stages of IC fabrication. The idea can further be adapted to high-end applications where ICs at the fabrication field are scanned, and based on the mole shape engraved, we can estimate the stage of fabrication. We can further implement our application to ensure that the mold pattern abides by design rules before it is applied onto the IC. Thank you.